In this video, I will introduce the first part of the fundamental theorem of calculus. I will present the statement and examples of how to use it, and I will leave the proof for the next video. The fundamental theorem of calculus establishes some connections between definite integrals and antiderivatives, two concepts that are defined separately and in principle are different, but they relate through this theorem. And it has two parts. The first part answers the question, what can we say about any function defined as an integral? And the second part answers the question, how do we compute a definite integral quickly? I'm going to focus for now just on the first part. Here is the precise statement of this theorem. I begin with an interval I and a real number a on I that I fixed. And then I also have a function little f with domain I. Then I define a new function, big F, by this equation. Big F of x is the integral from a to x of f of t dt. So big F is a function that is defined as an integral. If this notation is confusing, I suggest you rewatch the previous video in which I explain how to define functions as integrals. Now the theorem says that if little f is continuous, and notice that little f being continuous guarantees that it will be integrable, and therefore this expression makes sense and big F is well defined. So this is a valid way to define a function. If little f is continuous, then big F is differentiable and the derivative of big F is little f. In other words, big F is an antiderivative of little f. We can summarize this with words by saying that a function defined as an integral is an antiderivative. And that is it. This is the connection between the notion of antiderivative and integral, which again were defined separately, differently, but this theorem tells us that they are related. We can summarize this theorem with an equation. It's often written like this. I can say that for any real number x on the domain I, big F prime of x is equal to little f of x. Or equivalently, the derivative with respect to x of big F of x is little f of x. And now I can replace big F of x with its definition. And I get this equation, which is the common way to summarize it. The derivative with respect to x of the integral from a to x of f of t dt equals f of x. And it is important to notice how we use notation in this equation. Both the left side and the right side are functions of x, not of t. T is just the variable of integration, is not relevant and it disappears. Both sides are functions of x. On the left hand side I have a function of x, and the derivative with respect to x still a function of x. And so on the right hand side I also need to have a function of x. If you're attempting to change an x into a t or vice versa on one side or the other, not only it will be wrong, but it will make no sense. I'm going to present some examples of little calculations that we can do using this theorem. I invite you to pause the video after watching every question and try to solve it before watching the answer. You don't need any extra tools. You know everything you need to solve these problems. And any answer that you watch without attempting the problem is probably a learning opportunity wasted. I'll start with something short. I define the function big F of x as the integral from 1 to x of e to the minus t squared dt. What is the derivative at 2? Pause the video and try to answer it. There is not much to do here. This is a direct application of the theorem. The derivative of this function is the function in the integral, e to the minus x squared. So f prime of 2 is e to the minus 4. That's it. Second example. Now we're going to do it backwards. I want you to construct a function g such that its derivative is this rational function here, 1 over 1 plus x squared plus x to the 10, and g of 2 is 5. And you're going to have to write this function as an integral. So pause the video and try to write an answer. We know from the theorem that if I want to construct an antiderivative of a function, all I have to do is to write the integral for that function. So this suggests I try g of x as the integral from a number to x of the rational function inside. And I've chosen 2 because then I have control over the value of 2. If I do this, g of 2 will be 0. So if I simply add 5, now g of 2 will be 5. And this doesn't change the derivative, so the other condition is also satisfied. Example 3 is a bit more complicated. I now define the function big G of x as the integral from minus 4 to x squared, not just from minus 4 to x, of this function. Can you nevertheless calculate its derivative? I'll give you a hint. Use the chain rule. Pause the video and try to solve it. I won't present a full answer, but I'll just give you a hint of the difficult part. I'm going to compare this function with a new one, and I'll give it a name to be able to compare them, which is big f of x is the integral from -4 to x of the same function. Now, I chose this function because I do know what the derivative of big F is. F prime of x is, you can answer that. That's a direct application of the fundamental theorem of calculus. And we also know what the relation between f and g is. G of x is simply big F of x squared. So then to calculate the derivative of g, all I had to do is use the chain rule. So I trust that with this you can complete it. I leave the details as an exercise. Here's the final example. Now the function is more complex. Big H of x is the integral from x cubed plus 1 to x squared plus 2x of e to the minus t squared dt. Can you compute this derivative? I'll give you a hint. Try to break this into pieces and reduce it to a problem that you have already solved. Pause the video and try to answer it. Again, here is a hint. The function is defined this way, the integral from x cubed plus 1 to x squared plus 2x. I can separate this as the sum of two integrals. For example, the integral from 0 to x squared plus 2x, and the integral from x cubed plus 1 to 0. I chose 0 at random. I can put there any number I want, and this property of addition of pieces of integrals is true. And I don't need 0 to be between x cubed plus 1 and x squared plus 2x. This property is true no matter what the order of those two numbers is. And now I have written big H as the sum of two things. And the first thing, I know how to take its derivative, because it's an example like the previous one. And as for the second one, I can reverse the ends of integration if I multiply by -1. So now the function big H is the difference of two functions whose derivatives I know how to take. So I leave it as an exercise for you to finish it from here.